Hello, my name is Chris Ellerson. My wife and I founded Theodore's Heart Initiative after losing our son, Theodore, shortly after he was born. He passed away from a congenital heart defect that hadn't been detected before his delivery. Today would have been his first birthday, and it felt right to mark that day by showing what we've been building in his name. I'm not a clinician. I'm a parent who went looking for answers, and what I found is that Theodore's story is not rare. Congenital heart disease is one of the single most common birth defects in the world, and far too many cases it goes undetected before delivery. Not because the tools aren't there, but because getting the right image at the right moment is harder than most people realize. That's what we're trying to change. Every pregnant mother in a developed country receives a routine anatomy scan, typically around 20 weeks. A trained sonographer is already looking at the fetal heart during that appointment. The cardiac structures we need to evaluate are right there on the screen. The problem is that getting a diagnostic quality image of the fetal heart is genuinely difficult. The heart is small, it's moving constantly, and capturing each of the standard diagnostic views with the precision required for a confident assessment demands a level of skill and experience that isn't uniformly available, especially in under-resourced settings. To understand what we're building, it helps to understand what a thorough fetal cardiac assessment actually requires. It isn't a single image. The International Society of Ultrasound in Obstetrics and Gynecology guidelines define 4 standard diagnostic planes that a sonographer needs to capture cleanly in order to rule out the most common and most serious categories of congenital heart disease. The 4-chamber view. This is the foundational view and the one we're demonstrating today. It shows all 4 chambers of the heart, left and right atria, left and right ventricles, along with the wall between them and the valves connecting the chambers. A good 4-chamber view can catch conditions like ventricular septal defects, hypoplastic heart syndromes, and atrioventricular canal defects. It's included in most routine anatomy scans, but image quality is highly variable. The left ventricular outflow tract, or LVOT, rotating slightly from the 4-chamber view, this view shows the aorta as it exits the left ventricle. It's essential for identifying transposition of the great arteries and aortic stenosis, conditions that are life-threatening and time-sensitive, not caught before birth. It is this view that could have identified the blockage on Theodore's aorta found after birth. The right ventricular outflow tract, or RVOT, a complementary rotation to the other side, shows the pulmonary artery leaving the right ventricle. Together, the LVOT and RVOT catch conditions like tetralogy of fallout and pulmonary atresia that the 4-chamber view alone will miss. The 3-vessel view. Sometimes called the 3-vessel trachea view, this shows the relationship between the pulmonary artery, the aorta, the superior vena cava, and their position relative to the trachea. It helps identify chaortation of the aorta and other great vessel anomalies. Together, these 4 views give a comprehensive window into the fetal cardiac anomaly. Studies suggest that extending beyond the 4-chamber view alone increases CHD detection rates from roughly 40% to 70% or higher. What you're about to see is our first working version of an AI-assisted guided system built around exactly that framework. For this proof of concept, we're focused on the 4-chamber view. The 4-chamber view, which is both the most critical single view and one with the most available training data. The demo is running our live pipeline against a simulated video feed using genuine ultrasound images. The pipeline does 2 things simultaneously on every frame. First, a lightweight detection model, YOLO 11N, locates the fetal heart and draws a bounding box around it in real time. Second, a quality assessment model built on EfficientNet v2s analyzes the cropped region and rates the quality of what it sees against the expected 4-chamber view standard. The rating drives the color of the box on the screen. Green means the current frame is clean, diagnostically usable, 4-chamber image. Yellow means the heart is in frame, but the angle, clarity, or position need adjustment. Keep moving the probe. Red means the heart has been found, but the view is degraded or nothing has been detected at all. The goal is to give the technician an immediate eyes-on-screen signal so they can act on it in real time rather than discovering after the fact that a critical view was missed. I want to be clear about where this POC sits. The detection and quality assessment you've seen is trained on the 4-chamber view only. That's the data we have access to today through the focus data set available on Kaggle publicly. The targeting isn't perfect. The frame-by-frame nature of the current demo makes that visible. That's expected at this stage. We need additional data and additional views. What this demonstrates is that the two-model pipeline works. The architecture is sound, the signal is real. The next phase is expanding traded data to cover all 4 views, which requires the SonarNet dataset that we are optimistic will provide a more holistic amount of data, as well as the additional views that we're currently missing to be able to train the rest of those diagnostic views, as well as additional data volume so that we can get the precision rates higher and hopefully be just a little bit more accurate and smooth in the detection. And the pipeline isn't finished at stage 2. What will come next is to provide a diagnostic layer. What the first 2 models do is solve the hardest part of the physical problem, helping a technician reliably capture a clean diagnostically usable image of the required view. Once those 4 images exist, the third and final stage passes them to a highly capable medical reasoning model for diagnostic review. Models like Google's MedGemma are purpose-built for exactly this kind of task, analyzing the medical images and flagging structural anomalies that warrant further evaluation. The guidance system gets the right images, the diagnostic model reads them, a clinician reviews the flags. That's the full pipeline. Brings me to where we're going. The jump from a demo video to a live clinical tool involves solving several distinct engineering and regulatory problems. I want to walk through the honest shape of that challenge, the data connection. Ultrasound machines communicate using a standard called DICOM, Digital Imaging and Communications in Medicine. Getting a live frame feed out of a hospital-grade machine in a format our pipeline can consume requires either a DICOM integration at the software layer, or more practically for early development, a hardware video capture card sitting between the machine's video output and our processing system. The capture card approach is hardware agnostic and works with any machine regardless of manufacturer. Not all ultrasound machines are equal from an integration standpoint. Companies like Butterfly Network, who make the IQ handheld probe, have published open SDKs that give developers direct frame access that makes them a natural first target for a tethered prototype without needing a full hospital partnership to begin. Edge performance will be an important aspect of what we're doing. A system that requires a cloud round trip on every frame isn't viable in clinical environment. The model needs to run locally at 30 frames per second or better. That means optimizing for edge hardware. NVIDIA's Jetson devices, Intel's OpenVINO toolkit, or TensorRT on a dedicated GPU workstation at the point of care. The architecture we've chosen is deliberately lightweight for exactly this reason. So even in resource-restricted environments, we can get a local model running this application that pairs with the hardware. The regulatory path. Software that assists clinical decision-making is classified as medical device in the US. That means a 510K clearance or a de novo pathway through the FDA. In Europe, CE marking under the MDR. That process requires clinical validation data, documented safety analysis, and a quality management system. We're not there yet. We're not pretending to be. But the architecture decisions we're making now are being made with that pathway in mind. Theodore's Heart Initiative is a nonprofit. This work is driven by the belief that the technology to detect congenital heart disease earlier already exists, and the barrier to applying it isn't capability, it's access and attention. What we built today is a proof that the concept is real and the pipeline works. What we need next are clinical partners willing to collaborate on validation data, hardware partners who will help us test against live ultrasound streams, donors to help keep the dream afloat, and research collaborators who share our conviction that this belongs in every prenatal clinic, not just the ones that can afford a specialist. If any part of what you've seen today resonates with your work, we'd welcome the conversation. And thank you for your time.